Okay, so we are live. Hello, how are you doing? I hope you all have been great. So, what are we going to do today? Let's get this down real quick. So, what we're going to do today is we are going to study about semiconductors and solar energy. Now, as you might be aware of the global scenario in terms of energy, how energy uses is important to move us forward, and how energy usage using non-renewable resources is continuously destroying our planet, right? It's absolutely destroying our planet. So let's just study some things related to this. So I recently read about this. Okay, so we talk about this for a little bit. Until then, everyone can join the stream, right? So you see, US energy usage per capita, year wise, of any country for that, in India energy usage per capita year wise. So let's look at these graphs, right? So as you can see, the energy usage is seeing a recent decline in terms of per capita energy since 2010 in this graph. And if you see this graph, units uses energy information administration annual residential energy consumption per capita 1950. So it was constantly increasing, right? Which made sense because all of the households were uh, coming transitioning from uh, using lanterns and stuff to using electric bulbs, fans, and all of those technological advances that led to us now. But yeah, you can see that there was an increase in the energy usage, and we were continuously growing in terms of fundamental physics, right? But however, after 1970, somewhere around here, the energy usage somehow stagnated, right? The energy usage didn't increase uh, bit much after that. And why is that? I think that is because, like, why is that, right? Like, okay, let's look at the industrial revolution. Energy. So there was a very impressive graph that is so that how industrial revolution has always caused an exponential increase in the energy consumption, right? So it must be here somewhere. I don't know. But okay, so basically what the graph says is like this also makes sense, right? Since the industrial revolution, since every industrial revolution happened, we are currently in industry 4.0 phase, right? Where we are trying to introduce AI into the industries as well. So optimize the industries further and such kind of things. But okay, if we look at the general consumption, energy consumption, it has increased continuously, right? Like it shows the graph till 2000, but it's still growing. That makes sense, right? Because and the previous graph that I showed you was per capita, and I showed you the per capita graph because it gives insights on there is an increase in the population too, right? So we want to exclude that population dependence, population graph worldwide, right? So there is an exponential increase in the population too. So we have to account for that. And like this is crazy, right? How much the population is expected to increase. Like I don't think this is really sustainable. Like we need to figure out a way to stop this, right? We are in a very dreaded state at this number itself. So it is pretty ridiculous. So what I was trying to look at is so when we talk about the energy alternatives that we have available to us, renewable energy alternatives, some of the biggest names that come up to mind are wind energy, solar energy, geothermal energy, and I guess hydro energy is also really important. Like by hydel, I mean hydel energy. So hydel energy is the one that comes from dams, right? When you store water potential, and you use that the flow of that water to uh, generate electricity by running a turbine. So basically, a hydel power plant. So these are some of the first figures that comes to mind when you, yeah. I hope that figure makes you more sense. So these are some of the figures that comes up to mind as the most renounced, most announced renewable energy sources out there that are available to us. Right. So solar is one of them, and I was just going through it again as it's interesting to see how or what work can be done in solar energy as a domain to increase the optimization. I read some articles related to solar energy, one of which you might have heard yourself. There was a sunflower group, sunflower solar panels. So what they did was they made solar panels that follow the sun, right? So that made more optimum energy consumption. And there was some paper that also investigated the shape of the solar panel, right? The shape of solar panel and how the shape of solar panel might affect uh, the optimum energy absorption from the solar light, right? So shape of solar panel, how do I say it? What was it? Shape dependence solar on performance comparison, spiral shaped solar panels. Okay, I've not heard the spiral shaped one. If they have a figure available, they have no. See some other paper, right? Shape dependent solar thermal conversion properties. Solar thermal. Okay, let's look at this. This should make more sense. Wow, they literally have stopped using any. Or they have they? Like these are not the papers I was talking about. Like, okay, let me just sorry, the shape directly concave versus convex flat plate solar collector, right? So concentrating collector. The hell? Should I not say collector? Please. No, effective changing shape on the efficiency, right? So yeah, this is it. So yeah, we can read it at the front, right? So standard flat plate module showed an efficiency of 4.5 to 6%. Convex showed an efficiency of 0.8 to 1.2, while it was 0.46 to 0.53 for concave. Okay, so these are ridiculous results, right? Obviously, you will say, okay, so flat plate works best, no need to research it, or we're good. But there are varieties of shape that are available to us, and the shape dependence, or I think one of the factors to consider when you are trying to evaluate the shape of the solar collector to be used is the region you are in, right? Is the what global location you are at what month of the year, right? Because when you're talking about the shape of the solar collector, it will depend on the overall solar like what do we call it, like if you have heard about this solar plot, trajectory, solar path, right? Yeah, solar path diagram. See, so this goes to show the location of sun from a particular location of earth on a particular day of the year at a particular time. So this thing this thing is really important when you are talking about the shape of the solar collector, and the size of the solar plates you are talking about also becomes a factor, right? So in this research paper, I'm not sure if they have taken into consideration the location that they used for this kind of efficiency measurement. I believe that the shape would be heavily dependent on the like the particular location of the sun at that particular time, right? Or for that particular country, we can say that particular state, that particular region, in a sense, right? How the overall sun's location, solar path is for that particular region, is what I'm trying to say here. So yeah, all of this renewable energy sources, cool stuff. You right. So it is important to figure out a way we can find better renewable energy sources. Now, the target shouldn't necessarily be to reduce the energy consumption. It is important to reduce the energy consumption, but more importantly, it is important to increase the per energy output of a particular machine, a particular factory, a particular industry. That's what will bring us to a better future, right? If you are stopping energy consumption, you're literally stopping advancement. That's what we have seen through all these years. But I'm not saying that energy usage means we need to exploit the resources of our planet, right? Of the nature. It means we need to find energy resources that can sustain the planet as well as help us drive towards the future. So AI is a promising field there too. Like uh, Industry 4.0 is full of AI. Like because reinforcement learning cooling station. You must have read about this. How Google employed reinforcement learning for cooling station. Was it Google? Let's see. Controlling commercial cooling systems. Okay, yeah, it was DeepMind, right? Controlling commercial cooling systems using reinforcement learning. So they were able to increase the efficiency, energy savings of approximately 9% to 13%. Right. And they were able to do it just with the help of AI, just by controlling when to switch on a particular uh, air conditioner, for example, so that the energy usage is minimum, and at the same time it maintains the temperature requirements of the server. So that is what is necessary. We need to find sustainable sources of energy to develop the similar output or increased output using the same amount of energy, and the energy source should be cleaner, right? It shouldn't be a non-renewable burning that causes pollution kind of energy source. Rather, it should be comparatively cleaner. It doesn't necessarily need to be zero emission too. That is the target that we are trying to achieve, but that is a goal farther into the future, right? So the initial goal that comes out of this conversation is to find an energy source that is renewable, that allows us to increase the output or deliver the same output using less energy or cleaner energy, while at the same time we also want to focus on uh, working on new industries, right? Working on new industries that can advance us to the future. And it is clear, and it will always remain as a fact that new industries, new technologies, new ideas would require larger energy, right? They might not need that at the developed stage, after they have been gone through all of the phases, but during the initiation phase, during the prototyping, during the adoption of a new technology, you need higher energy requirements. You need higher energy requirements when you are trying to deploy uh, a newer innovative uh, technology in any field, that is in any field. And we will always be dependent on products, right? Physical products is a thing that can never go off. You will always require physical products to be able to interact, to be able to perform things. So you can improve the efficiency of a computer as much as you want. That would improve the time and energy requirements in terms of the computing abilities. But the production, when it comes to production, when it comes to producing physical products, you need to focus there too, right? So yeah, that was a lot talk regarding the same. So let's come back to what we are trying to do in this stream. So actually this is a very basic stream. I just wanted all of us to be on the same page. So I thought, why not just discuss everything that I am aware of in terms of semiconductors and solar energy till now, and then in the further streams when we try to read some research papers regarding solar energy and go through some of the content that focuses on solar energy, we might be more clear and get better ideas towards it, right? Because that's what we try to do here, right? In these streams, we are not trying to like, I'm not trying to like just teach you something. These streams are not just passive for you to watch. You can, and some of them might be like that, but the overall goal is to actively participate in conversations, discuss ideas, develop new things, right? That's what we are trying to do. Okay, a lot of chit chat. Now let's start talking about semiconductors. So I have my notes here. These are the notes I'll be using each semiconductors. I know they are a bit messy. I just try to write them in as small of an area as possible. um and I'll be discussing these, and I hope will be able to help you. So these are my notes from the JE Times itself. So it's been a while. I do remember the intuition regarding semiconductors and solar energy. I think it will take me a I'm not the best at it right now, but I I know enough to be able to teach. And then we'll learn more from the research papers that we'll read, right? The latest work that is going on. This is all like the traditional stuff that we'll be talking about here. So let's not worry too much about that. Okay, so yeah, let's talk about this. So first of all, let's talk about semiconductors. The things these so difficult to set up my drawing tablet here. But to create space for it. And yes, you can ask any questions during the stream. I'll be open to that. We can discuss some new things if you have a technology in mind too. I always enjoy exploring new ideas, challenging ideas. What we do here. Yeah, the reason I opened this channel is that too. So yeah, let's get started. So let's first talk about semiconductors. Right, that's the one thing we'll be majorly talking about here anyway when it comes to PV cells. Like I know there are solar collectors based on thermal energy too, but I think that is much more of a mechanical and material oriented research. Like uh, solar thermal collectors, for instance, solar thermal collectors, uh, their efficiency can also be improved using AI and programming. But I think if you want to focus on technologies that are really necessary, like electricity is the one thing that we have really mastered in the new years and exploited various properties that different devices such as inductors, conductors provide us to generate various outputs and convert it into various forms, logic gates, and all of these things that helps us to automate processes. Mostly comes from electric appliances in a sense, or electronics in a sense, right? So that's why mechatronics is such a big thing, right? And industry 4.0 is all AI, while industry 3.0 was all mechatronics. And the reason for that is because mechatronics allow us automation. Mechatronics is the thing that uh, why is mechatronics the thing that allows us easier automation? Well, the thing is, we have translated a lot of our things that we do in our day-to-day life in electricity, in a sense. When led brighten up using electricity, right? And we can control electricity using logic gates. These logic gates and a large compound of them with various transistors and various semiconductors form up a computer, form up a chip. This chip can control how the electricity flows, right? So all of these things are in, like, if you consider electricity as a language, like uh, during the previous times, like, right, all of the things were translated in terms of mechanical energy, right? When you talk about hydraulics, when you talk about pneumatic systems, when you talk about kinematic chains, these all are translations of mechanical energy from one form to another that is used to make various appliances that we see in our day-to-day lives. For example, bicycles, right? It was all the application of mechanical energy translation. But in the recent years, and the more advancement that we see nowadays, majorly from the integration of electricity. Most of the major things that we see in our day-to-day life are translated into electricity. When you light up a bulb, you're basically translating your wish to light up a bulb using a switch through the bulb, right? So that's what you're doing, and that's what you do when you're working with a computer too, right? Or when you're working with Wi-Fi, when you're talking about internet, all of these things are translated in one way to electricity too, right? Electromagnetic waves are traveling. Electromagnetic waves are inferred by a signal receiver. That signal receiver converts it into electrical signal. These electrical signals travel through various transistors and various semiconductors, various switches inside your computer that gives right to a particular data or command, all of those stuff. So most of the things are in electricity. So therefore, solar thermal conductors, as good as they are to improve the efficiency of various appliances. For example, if you have, let's take an example, right? So if an industry has a boiler, right? So it has a boiler that stays is open. Now the industry makes the boiler, generally makes the boiler out of a shiny substance. And what I say is, okay, the boiler is already kept in the open. What I'll do is I'll paint the whole boiler black. And why would I do so? I'll say my agreement will be I'm painting this boiler black because it will start absorbing the solar energy more efficiently because of its black color, because it will now be collecting, absorbing all of the various wavelengths of light that will be falling onto it. And I'll be able to say, okay, in some sense I'll increase the internal temperature of the boiler, and hence I'll have to provide less external heat. This will increase my efficiency. So this is a clean and a simple way to use solar thermal collectors, right? But when you want to specifically use and collect solar energy, it is not very practical to store thermal energy, because thermal energy can leak. You need perfect insulators. Perfect insulator doesn't exist. Then you will start talking about aerosol and stuff like that. And you know, it's just too expensive. Am I right? Is it aerosol, aerogel, something? I'm not sure. But okay, right. Like I'm basically talking about uh where you put where you use a polymer and you fill it with water, and then you use a vacuum to let all the water out from the pores, and it is left with air, right? And that is the best insulator that is known to us. I think it is, no, it's not aerosol. Aerosols, yeah, it's okay. It's silica aerogel, I think. Yeah, that's what it is. Silica aerogel. So what it is basically is it has a lot of pores inside of it, and we fill those. What do you want me to explain again, Roshan Raj? Can you ask in a bit more detail? Uh, I should continue with this while he's asking. So it has a lot of pores inside of it when we are talking about silica aerogel, right? And these pores are filled with air using a pressurized, there was some equipment. And yeah, it is the best insulator that is known to us. It is used in heat caps, heat caps nose for you know, space shuttles and stuff. Pretty cool stuff, really really cool material. So, you know, it is, and it is extremely expensive. So it is not very feasible to store thermal energy, right? It is not feasible to store thermal energy, but it is much more feasible to store electrical energy, right? Yeah, I'm gonna start explaining semiconductors. I have not explained semiconductors yet. Um, I was just talking a bit background of why we are talking about semiconductors themselves, why we are talking about PV cells in a sense, why we are talking about solar electrical energy, why is solar thermal energy not enough? That's what I'm trying to explain right now. Okay, we will come to it. We'll come to we'll start explaining semiconductors immediately. Okay, so yeah, all of this. I hope that this makes sense now, right? That uh, how is thermal and solar conductors, and these are more used in like for home applications, right? You can use thermal and collectors for home applications, like you want to heat water for bath, you want to uh, you know, keep your floors warm using solar thermal. Like there are appliances like that where you can you where you use wooden flooring, right? So beneath that wooden flooring you can have pipes laid out from which hot water will pass. That water would be heating using the solar energy, right? And then heated water would keep your floorboard warm. So these are some of the applications where you can use solar thermal energy. But when we are talking about on an industrial level, on a feasibility level, where you want to collect large amount of energy and need to store it, you need to think in terms of electricity, because that is the language we are using with most of our modern day appliances. And at the same time, solar electrical energy is more feasible to store, right? The storage requirements are much more convenient. You have multiple types of battery available. These batteries, nowadays lithium ion batteries, and there was some research, I think, on sodium ion batteries too, if I'm not wrong. That was really interesting. I have not read it completely. We can explore that when we will be talking about solar energy when we are talking about solar energy, we need to talk about storage and stuff too. Right now, we'll be talking about the collection phase only, but when we'll come to that, we can talk about this. So there was some sodium based um, battery too. Oh, there was some recent research into it. Okay, so let's start talking about semiconductors. So to understand semiconductors, let's start from where it all begins. Let's start from solids, right? Let's try to categorize solids and see where does semiconductor arise from. Okay, so for that, let's understand the band theory of solids, right? Okay. So what is the band theory of solids? So band theory, basically the bands we are talking about here are the energy bands. And let me draw a diagram first so that uh, you can see what I am seeing, can understand better. So it we have the interatomic distance here, and we have the like energy here. So what happens is, okay, so this is a bit from the SPDF thing. If you are aware of this, the what do we used to call this? Uh, I think they were called the hyper. Yeah, it was completely lost of this. Chemistry was not the best eyesight. But okay, so yeah, hybridization. Okay, now I instantly remember. So yeah, so the hybridization theory. So these are the various hybrids that are available, right? The SPDF hybrids. So what happens is, for example, let's see. So for um, particular atom, you have P hybridization and S hybridization, right? So we all know is that S is the lowest energy one and F is the highest energy one, right? In terms of the hybrid bands. So what happens is that when we are here and when we decrease the interatomic distance, the energy increases, right? Because there is a optimum distance, and after that and before that, the energy will decrease increase. And for S also, the energy increases. However, it looks a bit like this. Right, okay, so this is not dipping down. Let me visualize this correctly. So it is going straight for more closer time, but after that also peaks up, right? This is what it is like. And what happens in between here is there is some mixing of hybrids. So these different hybrids of that we have, hybrids of electron, these get mixed up in the middle somewhere, and then they got separated again. So this interatomic distance where they got mixed. So we have in the p state we have 6 electron states available to us, um, and in s we have 2 electron states, right? So what happens is, so this is where 8 of these states are all mixed up. Like you can't segregate them. What electrons contain consist of the p ones and what are the electrons that consist of were s before. You can't do that now. They are all mixed up, and these are the like our p and s ones. So the electrons that are in the p um, here, that are on the p side of hybridization, these form the conduction band. They are at a higher energy state. They can easily jump out of the valence bond, that is, and they are in the stored in the conduction band, right? And these are the ones, these electrons, uh, these electrons are stored in the um, valence band, right? And the middle part here that has no electrons, right? Right, and that I should have drawn them beneath each other. Let me correct that too, because we are talking about the atomic distance, that is the interatomic distance of a particular cell, that is right, of a particular atom. So this is the interatomic distance of our atom, and I am saying that this higher energy state is our conduction band, this lower energy state is our valence band, and the energy state in between both of these, this is the forbidden energy gap, right, Eg. So there are no electrons here. So what happens is, uh, when we talk about these conduction valence bands, right, that the conduction band electrons are the one that allows a atom to be conductive. This is the one that provides the electrons necessary to conduct electricity. And the valence band electrons are happily bonded in their respective bonds, and they do not want to jump out. You need to put a lot of energy to these valence bonds for them to be able to jump out of their atom. So they are stored there, right? They are in their happy state. Whereas conduction atoms do not require that much energy. You just provide electricity and they will start flowing with respect to that electricity, right? So for metals, this distance between conduction and valence band is practically zero electron volt. You need no energy to jump the valence band atoms to the higher band. They will jump automatically. And for inductors, we can understand, for inductors this energy is high. This is above 6 electron volts, we can generally consider, right? I might be a bit wrong on the figures here. Okay, so okay, above 0.3. Oh no, above 3. Okay, so this doesn't even matter. These figures are like, these are not rigid figures. These depend on atom and uh, particular conditions we are talking about. So let's say 3 electron volts, right? So the inductors, it is above 3 electron volts. For metals it is practically 0, and for semiconductors it is between 0 to 3. I hope it is visible what I'm typing, otherwise I'll increase the thickness of the pen again. Okay, and okay, again, silly mistake. These are not inductors, they are insulators. I don't know what's with me. Okay, cool. So we have insulators, we have semiconductors, we have metals. And this is the general consideration of how it works. Why a semiconductor actually becomes a semiconductor. Why? Because the energy gap is kind of low. And what happens is, uh, if we provide decent enough electricity, in those regards, if we provide an electricity that is an electromatic force of greater than 3 electron volts per atom, the atoms would be able to move freely, right? They will not provide any kind of insulation in some sense, in a practical sense. And now obviously all of those electrons would not be able to jump up, and there would not never be a case where there is 100% conduction, but you will be able to see a decent amount of current passing through it, right? That's what the intuition is. Now what we do is, now this is basically a semiconductor in its purest form, right? In its purest form. However, you don't use semiconductors in their pure form. The best parts about having a semiconductor, okay, so this is just the introduction part. Okay, what a semiconductor is, what are its property, where does it stand in terms of the different solids that are available to us. So there are the conductive solids, there are the insulated solids, and there are the semiconductive solids, right? That will insulate in most regards in 0 to 3 electron volts. But if you provide decent enough energy, they will be able to conduct too. So this is the introduction part of it, right? So let's go to the next page. And here, let's talk about extrinsic semiconductors, which are the most important ones. Because uh, when we talk about practical applications, this is the one that we use. We rarely use any intrinsic semiconductor. Intrinsic basically means the pure one, okay, that doesn't have any external, like, pollutant, you can say, in substance, dopant, we call it in terms of semiconductor. But it is basically a pollutant or alien kind of atom that we are introducing in our lattice of a semiconductor, so that we can vary the properties by our own needs, right? That's the main advantage that we have from semiconductor, that we can use different types of dopants to show different types of properties. So what are these dopants? So you can basically use a n type dopant and a p type dopant. Now what is this? So basically a p type is the one where you introduce a atom that has 3 electrons in its valence shell, whereas in n type you introduce an atom that has 5 electrons in its valence shell. So it which mean what it means is it has an extra electron, and this one has one less electron. So when it will be placed in the lattice, for example, here we have phosphorus, right? um, right, am I wrong? Hope I'm not wrong. Aluminium provides aluminium provides phosphorus is the nitrogen. I think this one. Okay, phosphorus. Yeah, yeah. So wait. So where is phosphorus, right? Phosphorus is with nitrogen, right? So with nitrogen would be, okay. Let's look up the periodic table. I've completely forgotten the periodic table. Right, here you go. So yeah, phosphorus is with nitrogen, right? It is a 7. So in the internal electron, so yeah, this is the pentavalent one. So in the internal electron, we only have space to accommodate 2 electrons. You must remember this, right? So we have 2, 8, 8, 18, right? That is something. I just remember it from Narrata of some. Yeah, it's all just the cramming memory that I have from chemistry. I was not really good at it. So yeah, so this is pentavalent, right? And in terms of trivalent, the atoms with the 3 electrons in their last electron. So basically, when two are accommodated in the internal shell, in the outer shell there will be three. So these are boron, aluminium, gallium, right? So let's come back to here. So here in the 5 electron ones, we have phosphorus, uh, As, SB, all of the things that we right now so in the periodic table. And here for 3 electrons we have, why do I keep writing pentavalent? So in the 3 electrons one we have aluminium, gallium, or boron, right? All of these stuffs. So okay, now we understand this. Now we understand there are two types of dopants that can be introduced. So what are the different properties that these types of dopant inflict? So okay, so what happens in an n-type dopant is it introduces a new electron in our semiconductor. So obviously, when we are introducing a new electron, the overall conductivity of the particular atom, particular element or semiconductor would increase. The conductivity will definitely increase, and the reason for that being uh, that there are more electrons that are free to travel now, right? So this makes sense because the number of electrons have increased. Now A similar effect can be seen in the p-type ones, right? Where we introduce atoms that have more holes in them because they have one less electron than needed to complete the bond, right? So what would happen is the overall conductivity would increase here too, but the conductivity will increase with the help of new holes, right? And the conductivity that would be provided by these new electrons and holes would be high enough that we can assume that the semiconductor itself was providing near to no electricity, right? Because they are they increase the conductivity by a decent significant amount, right? And let's just see how that this all of this conversation looks in terms of a lattice. So let's try to do our lattice. So we have okay, so we have um, 4 electrons in Si. So let's draw some silicon here, right? And let's say okay, so let's first talk about a trivalent one. So let's draw aluminum here. So we have a hole, we don't have an atom here, and we have 3 electrons, right? And then we'll draw simply all the silicon, and this electron is getting shared here, this electron is getting shared here, all good. Same would be happening from this side with some other silicon, same with this electron. And all of this is happening, this is also working great. uh, let's not draw the hole in this direction. Okay, so we have this, we have a hole, and all of this would be going on great. There will be sharing of electrons from each and every direction, and all of these will be living happily. The electrons would not want to jump out if there is not enough electric energy provided, and all of this is happening. But then we have this hole. This hole cannot join with anyone, so this is just there. What to do with this hole? So when we provide electricity, electricity flows from what direction? Negative to positive. So no, electrons flow from negative to positive, so electricity flows in the opposite direction. So electricity flows from positive to negative, so holes will move in the same direction. If we provide a electric field in this direction, the holes will start moving in the same direction, right? They will experience a force and they'll start moving, so the conduction will start happening. So this is what happens in a pentavalent state. Now for uh for a sorry, there's a this happens for a trivalent one. Now let's talk about the pentavalent one, right? So how do you copy things? I'm not sure. How do I copy this? Oh god. Okay, okay. Erasing two and copy. Oh, okay, cool. So now let's talk about pentavalent one. So let's change the color of the dopant. That's it. Now we have nitrogen. What happens when we have nitrogen in it? Nitrogen has a electron for this, so this would also be happening, no problem. But we also have an extra electron that is just there. So it is really easy to jump this electron to the conductance band because it is not connected with anyone. Nothing is stopping it, right? This electron. So what will happen is when an electric field is applied in this direction, the electron will start moving in this opposite direction. It will experience a force, and this will allow the semiconductor to conduct. So this is basically what the N-type and P-type form like, right? This is how the N-type and P-type Semiconductors basically conduct electricity, and this is the difference in their properties. So p type has a lot more holes in them, and we talk about n type, they have a lot more electrons in them. In terms of free, I'm talking about a lot more of free electrons and a lot more of free holes that can allow conduction. Right, so now let's talk about the one thing that is formed using these two types of extrinsic semiconductors that allows us to generate solar cells. Now let's talk about uh, p-n junction. Right. So as the name might suggest, in p-n junction we combine p-type semiconductor to n-type semiconductor end to end. Now how do we do this? Do we use welding and stuff like that? Nah, that's too complicated. What we do basically is we just use a single semiconductor. We dope half of it with the pentavalent and half of it using trivalent. That is just the basic insight of how it is manufactured. So now how do we use it? So basically, let's consider this is our p type, and let's consider this to be our n type. Right, so when we have a p type and n type like this, what happens is there are a lot more holes in here, and there are a lot of electrons in here. So uh, and there will be electrons here, there will be some free electrons here, but they will be very less in amount, right? And there will be some free holes here, but there will be only a few. Now what happens is, because of diffusion, because you know how when we store water in a vessel that is filled up and we use another vessel that is empty, the water keeps flowing out of this vessel till both of them are completely equal. In a similar way, these electrons wants to flow there, and the holes there wants to flow here because of these diffusion forces, right? Right, so that is also happen. What happens when the diffusion occurs? Okay, so what direction will the diffusion current be? So the electrons are trying to move in this direction from n to p, and the holes are trying to move in this direction from p to n. So the diffusion current would be in this direction, right? This is I diffusion because of diffusion. Right, but there is one more thing, one more phenomena that is happening. So there forms a depletion layer in between here. So what is the depletion layer? So there all the electrons start accumulating here, and the holes start accumulating here. After a while, a diffusion has occurred, and they have a electric force between them, right? So the force of their the direction of their electric force is this, from positive to negative, right? That's how the current flows, right? So this is the diffusion depletion current, right? And this is also known as the drift current. This this is formed in the depletion layer. This layer is known as the depletion layer, and the current is known as the drift current. Okay, cool. Right, so at start, the diffusion current, like this makes sense, like the diffusion occurs, diffusion current is greater than current caused due to drift, because not much of the holes are available in the n layer itself, right? And semiconductor, so there are not enough holes and electrons in the depletion layer that will cause a drift current. But as diffusion keeps on happening, after a while the diffusion currents become equal to drift current, and they are in equilibrium. So that's what the p-n junction in equilibrium looks like. So the I diffusion becomes equal to I drift after eventually I diffusion is equal to I drift. So that also makes sense. Now, when this has happened, right? So the repercussions of this is that when you'll try to uh, attach a forward bias in here, So for example, a forward bias is when we are connecting the positive terminal to the p some type semiconductor and the negative terminal to the n type semiconductor. So when you're doing this, there is a overall electric force in this direction. This electric force would be opposed by our drift current. However, it would be quite low. And when you provide good enough electricity, the limit would be around 0.7 electron volts only, right? And after this, when you provide a current that is greater than 0.7 electron volts, it will work as a conductor. It will basically start working as a conductor. You have enough holes and electrons to provide current, and it would work as a decent conductor, right? This is what happens. But when you talk about reverse bias, when you attach negative to the when you attach the negative side to the p semiconductor and the positive to the n semiconductor, what happens is you have an overall current flowing in this direction. Now you have the diffusion current flowing in this direction too, but the diffusion current, that is the diffusion color current, is in higher concentration, right? So what happens is all of the electricity that can be conducted is because of this drift current, right? Because the diffusion would work in the opposite direction, right? The diffusion wants to flow in this direction, so you are completely dependent on the drift one. Now the concentration of number of electrons and holes in the depletion region is much less when compared to the concentration of electrons in the p type and n type, and hence you will not be able to conduct much of a current, and you will need much higher electron volts to break this. Now we are talking as high as, like, what is there a figure that I have written over here? Yeah, I have not. But uh, from experiments I remember, I guess it's around 70 to 100 electron volts, so about 100 times higher, right? When compared to uh, forward biased current, right? I hope all of this makes sense till now. Right, so we have talked about two biases, forward configuration and a reverse configuration. In forward configuration, we connect the positive to the p type and negative to the n type. And what we are saying is it is easier for the current to flow in the forward bias because all the current would be flowing through diffusion. It will be favored by diffusion. There will be some opposition through drift. However, if you provide a current that is greater than 0.7 electron volts, the current will flow just like it flows in a normal conductor, because you have enough electrons and holes to allow the current to flow, right? But when it comes to the reverse bias, when you are connecting the negative terminal to the p side and the positive terminal to the n side, you are completely relying on the drift current to allow whatever conduction of current that is there, and therefore the current that flows is much lower, and in some case it can be considered practically zero, because the current flowed in reverse. Okay, so let me write this. So the current that flows in the forward bias is of milliampere orders, right? But when we talk about reverse bias, it's about microampere orders. But you can cause the breakdown, right? If you provide uh, in both cases, in forward there is the breakdown voltage is very less. You can consider this also the breakdown voltage, because if you provide a voltage which is lower than 0.7 electron volts, you will basically observe near to no current in your near to no current, because it will not conduct electricity, because drift current will be opposing the diffusion current and you will not be able to absorb much of electricity. However, when we talk about reverse bias, the breakdown voltage is 70 to 100 volts. So if you manage to provide a voltage that provides a force, electromagnetic force greater than 70 to 100 electron volts, it will cause a breakdown where the diffusion current will no longer be able to oppose the overall electric force that is being applied, and the electrons and holes will start flowing as per the voltage that you have applied, and therefore they will both work in the same way in that particular case. But however, in general application, this figures and this differences in their properties is what we use in different applications uh, to allow the current to flow or not allow current to flow as per different decisions to be made, right? So this is the basic introduction of how it works, and there are some basic graphs into it, so that's just for understanding point of view. So I hope this will help you understand whatever I have told you till now in a much greater detail. Let's talk about forward bias and reverse bias. So, right, in forward bias, you have a graph like this where, right, so this is your voltage, I think. Yep, this is your voltage, this is your current. So, after you have provided current that provides force greater than 0.7 electron volts, you will the current will increase significantly in terms of like practically the same voltage, right? Because now this must be confusing in a regard that it should be like this, right? Because the current increases its voltage, but we are talking about a limited number of electrons and holes here, so it will not like increase exponentially and continuously keep increasing with voltage. There would be a sudden shift when we are going from a voltage of less than 0.7 electron volts to a voltage of greater than 0.7 electron volts. But however, after that, there is a limit to electrons and holes that you are using, and therefore it will reach a constancy. This is what the forward bias looks like. However, in the reverse bias, what you have is, and we draw it in this axis because we are considering we are applying voltage in the opposite direction now. So, okay, so in this direction, in the reverse bias, am I right? Right. So there is some current, but that is in the microampere orders, right? This is right. So this is in the milliampere orders, right? When we're talking about now, what happens is, and this current voltage, and the current is in microampere. So there is a very low current that is going through it continuously, and after that, when you have reached 70 to 100 electron volts, there would be a sudden jump, and it would work the same way that it works in the forward bias, that your current would increase uh, with any voltage regardless, because uh, again there is a limit to the voltage that can be applied against them because of the number of electrons and holes that are available, but the current will start increasing suddenly, uh, just because we have a large jump of the available carriers, charge carriers, you can. So this is the basic of semiconductors that we need to understand solar energy. Now let's talk about solar cells. How does a basic solar cell works? So this is really easy to understand after we have gone through all of the semiconductors. Then this will be the basic part. Right, solar energy. How does solar energy work? So in solar energy, again specifying, we have two different forms of solar energy. We can have solar thermal energy, that is comparatively simpler to understand. However, it is difficult to store thermal energy, and it is not very feasible when we are talking about large amounts of energy. But when we talk about large arrays of solar PV cells that can store energy in terms of electricity, we are in a far better shape because we are using the properties of semiconductors, p-n junctions to be specific, that we just studied. Um, p-n junctions specific, and using these properties to directly convert solar energy into electricity. Right, that's why solar PV cells are more announced, more famous, or more heard of. You you might not have heard of technologies based on solar thermal energy in your day-to-day life. I don't think I would have known about it if I hadn't studied solar energy as an elective. But solar PV cells, you see them every day. You have seen them with your own eyes, right? All the cells that you see at rooftops and stuff, those are PV cells. You wouldn't see solar collectors that often. Yeah, you might have seen a solar cooker. I don't know. I'm not sure. But the solar cooker works on the principle of solar thermal energy. So they are very similar regards in regards of the principle that they are using, not in the regards of how they are working, because other solar thermal technologies are also dependent on fluids, right? Where we store the heat in a fluid, then we store the fluid in an insulated tank so that that thermal energy can be stored. And in terms of solar cooker, you are basically directly providing that heat to the food you are trying to cook. So yeah, all of that stuff. Now let's talk about solar PV cells. So what is happening in solar PV cells is, right, so first of all, you keep the N side on top. This is how you basically draw a solar cell, PV cell, a single PV cell. We are not drawing a solar array here. Solar array is when large number of PV cells are connected in series and parallel according to the voltage and current requirements to be met. Right. So this is the N type and this is the P type semiconductor. We use a thin N type. Uh, I'll explain more of this later. So what we are basically trying to do is we are making the N layer so thin, so thin. So okay, let's talk about the principles first. I don't know why I'm starting with diagram. Okay, so let's start with a simpler diagram. This is much simpler than what I. So this is your depletion layer, right? And this is your P type, this is your N type. So what happens is when electricity, uh, when light falls, a light of specific energy that has large enough energy falls in the depletion layer, it generates a electron hole pair. Now I talked to you about this when we were talking about the band energy of electrons, atoms. Basically, that there is a band energy, right? And if you provide enough energy, the valence band electrons would also jump in the valence band. And when those electrons jump in the conductance band, basically from the valence band, they leave a hole behind. So now you have two different charge carriers available to you at the same time, an electron and a hole. So when you're throwing electricity at the depletion layer of a PN junction, there will be a generation of electron hole pair, and this electron hole pair will increase the, will can be used to provide electricity, right? Because this electron hole pair that is generated will separate because of the diffusion current, right? So what happens is, let me see, right, okay, so what happens is when we connect it to appliance, so the P terminal, it is generally used in a forward configuration, right? So the P is considered as the positive terminal and the N type is considered as the negative terminal. And what happens is that the electrons are going from the N type to the P type as the electrons travel opposite direction to the electricity, and the holes are traveling in this direction, and therefore electricity is produced and there is a voltage among them. And why is this voltage produced? Because a new electron hole pair has been generated, and this electron hole pair generated would move in these directions because of the diffusion current, right? We remember the direction of the diffusion current, right? I diffusion. And we also remember that uh, in an equilibrium state, when we didn't had two different junctions, and we just generated a new junction, when we just generated the p and n type p and n type diodes, there is initially just diffusion current, there is no drift current, because drift current generates in opposition to diffusion current because a large number of electrons and holes start accumulating near the location of diffusion. So that creates a current in the opposite direction. So diffusion current gives birth to drift current and it works in the opposite direction. However, when you have introduced a new electron hole pair, it will move. Now you have introduced instability, right? So when you have introduced instability into a stable system, the diffusion current will work initially and the drift current will be generated afterwards, but it will not be as significant right now, because when the electrons would move in the opposite direction, they will provide a voltage and they are not stored in the system. The system becomes stable again. That's why the amount of time till you are providing light to the depletion layer is the only amount of time till when the electron and hole pair will be generated. After that, it will stop. If you stop the light, right, the electron hole pair generation will stop immediately. The electron hole pair that were generated would separate in some milliseconds itself, and the voltage produced will go away, right? So this is how solar cells basically work. This is the basic intuition behind them. And now, why do we keep the n thin and all of those basic things, right? So it's just nothing, it's just a bit of a trick that we use, that we keep the n so thin that it is thinner than half the depletion thickness. So depletion thickness is this, right? The total thickness of the depletion layer that was formed. Now we keep the n layer so thin that it is thinner than the depletion layer, or as thin as the depletion layer. Hence, this surface of the n side of a semiconductor, this surface can also be used for solar light. If the solar light falls on this region, it will be in a sense of falling on the depletion layer itself. So the electron hole pair that would be generated would be used for electricity. So that's why, that's the reason that we keep the n thin and p here, and the electron falls on this side. Okay, so that is all that is to it. And yeah, so we take energy from here and from here, and the p acts as a positive terminal and acts as a negative terminal. And I hope the intuition is clear why it is working like, why is p working like a positive terminal and working like a negative terminal, again because of the diffusion current. And why is the diffusion current working, why is not a drift current working? Because when we initially generated the PN junction, there was only diffusion current, and the diffusion current was because of the different concentrations of number of electrons and number of holes in the p side and the n side. And when we joined both of them, there was a diffusion current. However, because of the diffusion current, drift current was generated in response to it, as a large number of holes were at the wall of the n type and a large number of electrons were at the wall of the p type. And this caused a opposite electromotive force in the opposite direction of diffusion current, and it kept growing with time at a stage until and unless it was equal to the diffusion current itself, and that was the stable system. However, when we have generated a new electron hole pair in our depletion layer, this will move as per the diffusion current only. And if given some time, like, the current will only be generated till there are electron hole pair keeps getting generated, because those are the uh, like introductions of instability. If the electron hole pairs stop generating, if we stop providing light, there is no instability in the system, and the current would be equal to the diffusion current. Eventually it might take some milliseconds and everything would be fine, there would be no current. But when the light falls into the depletion layer and the energy of light is enough to jump the electrons from the valence band to the conductance band, we have electrons and hole pairs newly generated, that causes that instability, that causes all of this energy production, electricity production. I hope that summarized all of this, right? And again, these PN injections are heavily doped, and there are a few figures that I have written over here. I don't think these figures might be the most modern figures. There is a, again, as mentioned earlier, and why we are doing all of this, there is a lot of research that is going on into all of this. So as per material, like there are monocrystalline silicon, polycrystalline silicon, and amorphous silicon, I think, was also used in some cases. I'm not entirely sure of it. So all of this variety of stuff that is available to us, right? So we can't be entirely sure in regards of uh yeah, sorry. Yeah, so I was saying that we can't be entirely sure in regards to what are these figures, but it is basically mentioned that the p is around 300 micrometers, and the n is about 0.3 micrometers. So there is a thousand order difference between both of these. And I hope I have made it intuitive enough, right? I hope the whole intuition between the behind the diffusion current and the drift current and the electron hole pair generation. So basically, there are two steps to it. First step, use a different color for it, the highlighted one. First is the electron hole pair generation. This happens in our depletion layer, and second, the electron hole pair separation because of the diffusion current, right? And this Both of these phenomena allows us to collect solar energy, right? So that is completes our discussion on how solar energy actually works. I hope I was able to explain you all of that. It got very long. I think I took a large time doing so, but it's cool. It is okay to take some time behind this, and I know there's all the theory. This all of this theory is available on the internet, and there were various resources you can learn it from. I might not have been the best one to teach them, and I can share this document that has been generated. Right, all of these pages. I don't know if they will do you any good or not, but if you want them, you can have them. But how many pages did we took? We took 4 pages only. Okay, that's cool. That doesn't think. I don't think I took that long. How long did I? How long is the stream going on? Okay, let's exit this. It is saved, right? Okay. Okay, it's saved. Let's rename this. Can I rename? Oh God, I need. Let's export this. Blah. Color. Cool. So I can share this if you want. Okay. Now we have understood how solar energy actually works from the fundamentals of it, from the crux of it. And I think the intuition behind it is clear now. Now we can think about the various other stuff, right? So one of the ideas that I had in my childhood, and I still think about it sometimes, is like, what if we are able to design a material that has the, like, okay, let me show it to you. Like, so um solar what we call it, wavelength light needed for silicon. Okay, so for the silicon solar cell to operate, the wavelength of light needed is around 400 to 1100 nanometer. Now, it depends on the material, because as I said, the depletion layer generates an electron hole pair, right? So it depends on the material, that how freely available is its electron, how easily can it jump from the valence band to the conductance band, so that it can be used for conduction, right? So that it can be used for electricity generation in regards to solar cell, right? In regards to generating a voltage among the two terminals, right? That makes sense. So when we talk about gallium, right? Is it gallium? It's germanium. Uh, Germanium wavelength. Uh, Now let's talk about germanium. So yeah, so must be here somewhere. Okay, so really, okay, let's talk about the what it used to. Okay, so here it is written that iodine requires the least energy. So let's see, wavelength excite iodine for conduction. Absorption spectrum of iodine. So okay, so Right. So why we have jumped into a spectroscopy? So right. So what happens is when light falls onto a electron, if the light is of enough energy that is required for the electron to jump, the electron would jump from the atom because of that light. So that's the thing we use. Like that is the reason why cosmic rays and other rays are so harmful, right? Because they have a very high frequency and a very low wavelength, right? So yeah, okay, that makes sense. So what is the energy, right? If you know of the energy formula between a light and a electron, the is hc by mu, where lambda hc by lambda, where lambda is the wavelength. So it is inversely proportional to wavelength, right? So the higher the wavelength, the lower the energy available to you. So cosmic rays, etc., have a very low wavelength. They have a very high frequency. So what happens because of that is they can easily penetrate, excite the electrons inside the atoms of our cells, and somehow completely disintegrate you. Some sense, leave all your atoms unstable. So that's why all of these things are very dangerous. And yeah, in a fundamental level, that's what they are doing, right? And when we talk about why am I talking about wavelength in terms of semiconductors, is that if we have a particular material that has such low energy requirements for electron excitation, such low energy requirements that it can excite a electron with the help of just infrared energy, right? If we are able to generate a material that has such low energy requirements that it can be easily excited with the help of uh, infrared rays, then we can basically generate a electricity generator that uses the infrared rays that are emitted by human beings and convert them into electricity. And this will not be harmful to us in any regard, because the infrared energy that we are emitting just happens to happen because of the temperature difference between our internal body and the external temperature. So what is happening is these rays are constantly emitted from our body no matter what we do. As I'm wearing this sweater right now, this is warm from inside, because the sweater is what the sweater basically doing is it is storing the infrared rays that are released by my body. It is not letting them those rays pass on to the environment. Rather, it is keeping it between the sweater and my body, and therefore uh, the heat starts to generate and it keeps it warm, right? It is basically insulating those rays. That's what it is doing. So if we are able to make a material that requires such low uh, energy for electron hole generation, as we talked in solar energy, we can basically make a electricity generation that uses human infrared rays that are constantly emitted from our body. Most of our most of the calories of our body that are burned are because of these infrared rays. About, like, if you are eating 2000 calories, about 1500 or 1800 of those calories would be burned just from this. Like, you have exercise, right? You have all exercise, high intensity workout, completely highly intensive, most intense workout ever, calorie burn. Let's see the world record of calorie burn through workout. It's 452, 421 calories burned. Like, for how long? Okay, this is not really helpful. And like, for how long? Per hour. Like, if you keep doing push-ups for an hour, like, try doing push-ups for a minute. You will understand how difficult it can be. Like, you can do push-ups for 5 minutes. I think it is not that big of a deal. But if you keep doing push-ups for 1 hour, then you will be able to burn 420 calories. Now, how much workout do you think you do in a whole day? Like, in 16 hours, 8 hours of sleep, right? You burn very less calories from working out in terms of sleep while you're sleeping. And most of the times you're just sitting around. So you're burning around 400 calories a day, and you're eating 2000 calories, for instance. So 1600 calories that are going away are just from the infrared rays that are emitted from your body. Basically, if you are able to generate a material that has such low energy requirements for electron excitation, that an electron hole pair is generated just from the infrared rays of your body, you're basically able to generate a machine that can generate electricity using your infrared rays itself. And that is pretty cool, right? That is something to think about. If you are able to that requires a lot intensive knowledge in terms of material science, I'll say. It is not much in regards to research in terms of, like, you can work in the there are two ways to approach this, right? There are two ways to approach this. The first approach is using a material, right? Using a better material that requires less energy to excite. And the second is much more wishful or optimistic, I'll say, and I don't think it is even possible. If I talk up to a scientist or someone who is good in rays, they will just completely deny it. But the second approach would be to somehow combine these two rays, like combine multiple rays of low energy that our body is generating. For example, if we are emitting 1600 calories of rays, so we basically use some kind of a system that halves it, right, in some basic mathematics, and combines these two layers in some sense, and this 800 calorie energy is used in the atoms to excite the electron. So we can also use materials that don't have such low energy requirements, but we somehow combine our layers, reduce the efficiency, and in less efficiency able to produce electricity using these infrared rays. So this is an interesting idea, right? So yeah, so these are the two ways to approach this. The second one, I'll think, is more wishful, and I don't even think it's possible, because you can combine rays to increase their amplitude, to increase their um, I don't know, like change their phases, increase their amplitude. What else does a wave have? To change their direction, stuff like that. But you can't really change the frequency of a wave just by combining two different waves, right? If you have two waves of low frequency, you can't combine them to have a wave of a larger frequency. I don't. At least I think that is not. I don't know. Yeah, that would be pretty interesting to think about. And yeah, so that is one idea that comes to mind from all of this, from scratch study of solar panels. And yeah, so what I wanted to basically research with or work with was that, right, so as I talked to you about earlier, um right, so these rays are falling in on our flat plate collector, and it needs to fall on the depletion layer, right? And it can fall in any orientation, right? Does the orientation matter? Let's From what we have studied, it doesn't look like that orientation of the ray really matters. If the ray falls in from like this, if this is our flat plate collector, or if this is our PV cell that we just studied, this is the n n surface of our PV cell that is so thin that it comprises of the depletion layer too. So if we have this arrangement, and if a ray falls from this direction, and if a ray falls from this direction, I don't think there should be any difference between the two rays, because the electron hole pair should be generated regardless, because it is falling on the material, and the ray has enough frequency to excite the electron from the atom, from the depletion layer, and that should work, right? From what we have studied, this should be possible, right? And so that is the case. I was thinking of working on a project where we can simulate the solar path. That's the first target to achieve. The first target is to write a program that can somehow stimulate the solar path diagram, and use that to somehow predict the yearly uh, solar energy that can be achieved from a particular area in terms of the whole earth, using the latitude and longitude, and to predict the total solar energy that can be produced from that particular region. uh, by using the solar path diagram, right? Because it is dependent on the solar path diagram, and it is dependent on the region. So for a whole year, we can predict using the solar path diagram what would be the overall energy that we can expect from a particular arrangement of solar panels in a particular region in terms of the whole earth, right? Because when we are using a solar path diagram, it gives us the data. Let me show you the solar path diagram again. If I have it open somewhere, otherwise I'll search for it. So the solar path diagram, right? So it gives you data about the location of sun with regards to the longitude and latitude, with regards to the day, with regards to the month of the year, the day of the year, the time of that particular day. So all of this data is available to you. So you can use this data to simulate or predict basically what would be the particular energy that can be generated in a particular region in a whole year using all of this. But I think the one more factor that would be needed when we are doing this. So okay, let's type this some. Can we use open it to type things? Let's see. Let's open our same document if we can. Documents. Can I open this? Yeah. Cool. Can we type here? Stylus. So basically, what I'm saying is one of the factors that is needed, the solar path diagram, which gives us things that the solar path diagram provides us, is location of sun with respect to time, day, month, or and if you have all of this data available to you, you will also need what we is the weather data, because right, the clouds, rain, all of this thing will affect the solar energy that you will be able to collect. So you need weather data and the solar path diagram to predict, and you can use this to predict the solar energy that is produced. So that is one of the project that I was interested in working on. Predict solar energy produced in a year. In a year. Okay. So this is the one of the projects that I had in mind in regards to solar. And then I also wanted to work on regards to, as I was saying earlier, if we are able to achieve this, if we are able to predict solar energy, now we are doing this for only flat plate collectors, right? Now, flat plate collectors are like they require less space, but we have other shapes available to us that are able to provide with much larger area with less parameter, right? Let's think about this. Oh, okay. What do we do with this? So, what is the parameter? So if I draw xy and we have a line x plus, is this x equal to y? And yeah, so the parameter of the triangle form would be Okay, so explain. My idea is that perimeter and area of a particular shape are not entirely independent of each other, but they are also not entirely dependent. So we can have different shapes that can have much larger area for the collection of solar energy and need less parameter, so that what that basically with higher packing efficiency in some regards, like some kind of that. So we can use a different shape of solar panels, or a better shape that improves the efficiency of the solar panels in terms of packing, in terms of their area requirements. And they in less area they provide larger area for absorption. So for example, in terms of the collector type, when we talk about the collector, thermal collectors, so we have a type of solar panels that are concentrating, right, that require less area for receiving the thermal energy, as they are able to concentrate a larger area of solar energy using different techniques, right? So we have disc shaped solar collector which is able to collect all of this energy here, and we just have a receiver here. So this can allow us to reduce the overall area needs, right? So we can have a mirror plus solar panel arrangement, um mirror plus solar panel arrangement. So I we are able to make somehow a simulation or a basic model that can first use these two parameters to do for a flat plate collector. Then we introduce the configurations that define a flat plate to be a flat plate, right, as parameters too. Then that can allow us to find the most optimum configuration, or you can say, what by configuration here I mean the shape, the most uh, optimum shape that can store, that can collect solar energy from sun using a shape that is most optimum for exciting or generating the most electron hole pairs, or in that sense, generating the most electricity, simply put, in a year for a particular location. Location is also a factor, right? That what latitude and longitude you are talking about. So we can have different shapes for different countries based on their latitude and longitude equation, and how is the sun path for their particular country, right? That is also an idea. That is one of the ideas that I really want to work about. That is the idea that encouraged me to do stream, to talk about solar panels and such. That is interesting, right? But okay, this was just an introductory. I wanted this to be an introductory. So these are the ideas I want to work on. Hmm. English. Somewhat. I consider it a simulation because I think we might not be able to find a robust solution to put everything as a equation when we are talking about flat plate, right? When we are talking about shape, I'm not sure if we'll be entirely able to put the shape as a mathematical expression. So for those regards, I think of randomness based, yeah, like algorithms, and that's why I call it a simulation, that using some form of a simulation on shapes, solar power diagram, and whether we can come up through through some optimizing algorithm such as genetic or neural networks to a shape that is the best to accommodate the largest amount of uh, solar energy. And then we can also work on, and we can also introduce other factors such as packing. Like, you will not be able to produce a single large enough shape, right? That would not be very scalable. It will be more scalable if we have small such shapes that can be packed efficiently without leaving much waste space in between or gaps. So There is also a thing. That's why I think circle is not a good option, regardless, right? Because you think of circles, you think circle is a very optimum shape in regards to its area and parameter, right? But again, circles cannot be packed efficiently. They will leave gaps. So you need to find shapes that fit, more geometric shapes, more shapes with straight line. I think straight lines, yeah, straight lines, or or maybe I don't know, some weird puzzle like shapes. But they will be much difficult to manufacture, right? So you also have to think about the manufacturability, packing, and manufacturability. So there are a lot of factors that goes inside of it, right? It is not as straightforward. So, but this is straightforward. This initial idea, just going from here to here. This is pretty straightforward. So we can start working on this. Um, and yeah, this was majorly all that I wanted to discuss in this stream. And I think I was able to explain you well what solar energy is and what how semiconductors work, in a sense that they are able to make solar cells. How it slowly developed on the ideas of, first we understood how what different types of solids do we have and how do they work, right? What is their location? What is their position in their band theory of solids in regards to their energy, in terms of their conduction energy, valence energy, and the energy gap that is available when different hybridizations combine after a specific interatomic distance. There was that. Then we talked about this is the second page now. I want you to be the last. So yeah, the second page we talked about the extrinsic semiconductors, which are the most commonly used semiconductors. We talked about pentavalent and trivalent there, and how the pentavalent one introduces a new electron in the whole configuration, whereas the trivalent one introduces a new hole. And both of these are charge carriers. So when electric field will be applied, they will move in the respective directions based on their charge and would allow the semiconductor to conduct electricity. Then we talked about p-n junction. When we combine both of these, p type and n type, end to end, what happens there. So we talked about their diffusion current is initiated at the start, then there is a drift current that is generated in opposed to the diffusion current, and how that affects the forward and reverse bias in regards to the energy that needs to be provided for current to flow in both directions, and for the usability of charge carriers, because the drift current mostly manages to oppose the current. So therefore in reverse bias you need to apply a much larger voltage, because there the diffusion current will be opposing the current, and the drift current will be the only current that will work in the reverse bias direction. So there are limited number of electrons there, so you need to break away the diffusion current, which is larger generally, but at the equilibrium state the diffusion and drift current manages to be equal. So that was the basic intuition behind it, how it is working. Then we talked about solar energy. Here we talked about how we have two different energy methods, but why electric method is much more uh, feasible in terms of industrial applications, and we also discussed that before too. And then we talked about how a solar panel works. When we provide light to the depletion layer, electron hole pairs are generated, then they are separated, and the voltage difference is created. And we talked about how n type is kept thin so that a larger surface area for the depletion layer can be generated. And then we just discussed some ideas regarding it. First of all, we discussed the idea of generating electricity using infrared energy of emitted by humans and different animals. That would be great, but the limitations there, or the thing that is stopping us from doing that, is the material. A material that can excite just by infrared energy, because infrared energy has a very low frequency, or you can say very large wavelength. That amount of wavelength is not enough to excite any electron to the conductance band. So there will be no electron hole pair generation when we are talking about infrared energy. When we are talking about general materials that are available to us, we need to think about a material that can do that. And other than that, uh, the second approach we discussed to do that was somehow combining two rays and increasing their frequency. But again, I said it is nearly impossible. I don't think it has been possible yet. Maybe I'm not sure. Maybe I'm not aware of what is happening in terms of race. But that was the interesting part, right? That is where I started the stream from, when we were exploring the different things. Like, there has been a large increase in terms of the research or exploration that is being done in regards to fundamental physics. You don't see much papers published in regards to fundamental physics or fundamental chemistry or fundamental maths now. It is all based on applications. It is all based on use cases. Like, that is important. But I think the leaving behind the fundamentals, or not working on them anymore, thinking they have been developed enough, or we are not even close in terms of fundamentals, right? We don't understand quantum mechanics, we don't understand space. Half of the things are causing exceptions every now and then. Half of the discoveries, half of the observation in terms of space exploits what we have been discussed through the theories that we have proposed. And yeah, I think more people should get involved in it. And I'm not saying there is no research that is going on in that area, but I think it is less active as compared to how it was in terms of the 1900s, 1800s, all of those golden eras where we generated most of the revolutionary ideas that we are still using to this date. uh, yeah, that is something to think about in terms of material science too, right? In terms of material science, in terms of ray optics, the other approach I talked about. Then I also talked about a project idea that I had recently, where we can use the solar path diagram and the weather data of past records to predict the solar energy produced in a particular area using the latitude longitude of that region. Right, so we can predict the yearly energy that can be produced from that particular area, you using the weather data too, right? Yeah, and then we can somehow use this, increase the number of parameters that we have. We first do this for the flat plate collector, which is the most common, when we can get a lot of data regarding this. Then we can introduce the shape as a parameter itself, so that we can experiment with different shapes, and also try to find a optimum shape that generates, or has the best performance, best efficiency in regards to solar energy generation. So yeah, those are all the things that we discuss in the stream. And I think this is where I would like to end the stream. I hope it was informative. I hope you had no doubts in regards to semiconductors and solar energy after this. Uh, but we might be discussing this further, because I have to work on this. I have to work on some research papers. We might have a stream recently, where we can discuss different papers that are being published in regards to solar energy, some latest research. We'll read them, we'll explore what is going on to understand the frontier of science in regards to solar energy better. And a lot of work must be going on in terms of AI too, combining AI with solar energy, because that is whole that is happening in name of Industry 4.0. We are trying to combine everything with AI, and I'm pretty sure that must be going on with solar energy too. So yeah, we will do a stream where we will discuss all the papers regarding solar energy that are currently being published. There will be a lot of variables in them, and this knowledge that we have discussed might not be enough to understand those papers. But I think this, what we discussed, whatever we discussed in the stream, was a good base to develop a good point, so that we can be on the same page. And later can discuss that. We can discuss these papers, and we'll be on the same page. We'll be on the same knowledge base, and then we can search more information that comes through on our way, and learn according to that, and work on a new research paper regarding the solar panels and solar energy. And okay, not solar panels. Maybe we'll figure out a way to not use panels. I don't know, but okay, that's cool. Okay, yeah. Bye bye then. Have a great day. Have your lunch.